interesting and relatively accessible class. So we have a mixture here of undergrads and grad students. So I think that this sometimes we're going to see topics that are a little easy for the grad student crowd and sometimes a little difficult for the undergrads. So bear with the topics, but everything should be accessible to all of you. So if there is something obviously that you don't understand or you have problems with, please do let me know, right? So we can address them, these problems earlier rather than later. We're going to cover 3 main topics in this class. We're going to start with photogrammetry, everything that has to do with geometry, basically. Then we're going to go into radiometry, which is anything that has to do with light. And we're going to have a final component, which is a more formal description of functions, vectors, tensors, and so on. It's going to allow us to define the algorithms that we have seen earlier in the course more formally. It's also going to allow us to talk about image compression and other topics that are very popular in image processing, very necessary in today's world. We're going to open the Carmen sometime tomorrow. So there's going to be the syllabus with all the information. It's the same as the standard syllabus that it's available in the ECU website. So that is basically the syllabus. We will have lots of homeworks, projects in the class. So make sure that you turn them in time. There's going to be, everything's going to be announced and posted in Carmen. So make sure that you check this regularly. All the homework will be posted electronically in Carmen. You need to turn in the homework and the projects in Carmen by the date and time that is set in Carmen, right? Carmen automatically closes the window for uploading your homework and projects. It used to be the case that it was, here in class, you turn it in, hand it out as a paper copy. And if you were 5 minutes late, I was still here. There's no problem. But now Carmen is like, it's that time. It's that time. It just goes. So make sure that that doesn't happen to you, that you're just 10 seconds late or a minute late. All right. There's going to be a midterm and maybe a final, but hopefully not. We'll see, to be decided. We usually have a final project or we used to, a long time ago, used to have a final project for this class instead of a final exam. The problem is that with 80+ students, it's like almost impossible to do a final project and have them evaluated in time for final grades to be posted. So we'll have to work out something. We'll think about it depending on how the course evolves, okay? Because this is a very practical class, I encourage you to work in groups, to work with your friends, with your classmates, to both study the material, but also to work on the projects and homework. Having said that, be extra careful that it's okay. You need to understand that it's okay to work with others to understand the material, but that at the end of the day, it's you who has to write down the answers, work out the problem, work out the algorithm or implement the algorithm that needs to be implemented to run a project, and turn in your own work, okay? There are a set of rules to follow. All the misconduct criteria are stated in the syllabus. Make sure that you read that and you understand this. Fortunately, last time that we taught this course, there were 3 students that had to be reported to the university. So hopefully that's not going to happen again. Be very careful. There are tools these days that we use to know whether parts of a code have been copied from another student, another website. You cannot use, unless I say so, right? I mean, if they, or not I say so, the PDF that describes the project or the homework in Carmen specifically states you can use available code that's in this website or in any website or what have you. Unless it's specified, it means that you have to implement your own code, right? Don't go out there and try to find out who else has implemented this and just download that and use that code, because that's not the purpose of the homework, right? And as I was saying, there are plenty of tools these days to know whether you have done this, and obviously we use these tools because they are available. So just please don't do it. You're here to learn, so let's take advantage of that. We do use a book. It's called Computer Vision: A Modern Approach by Forsyth and Pons. This is the second edition of the book. Either the first or second edition is fine. It's also available online. You don't need to buy the book, although I recommend you have a copy available at somewhere. There are copies in the library if you want to. I followed the book relatively closely the first 1/3 of the course, less so in the second third, and not at all, obviously, in the last third, because it doesn't cover those topics, okay? I use another book that I will mention at that time when we get into that. I will also sometimes maybe draw some homework from this book or other books, but you don't have to have the book, because I'll just write down the actual question and all the details in a PDF file and posted it in Carmen, right? Okay. Any questions before we get started? No? All right. So, as I said, we're going to cover 3 main topics in this class. They're about equal length. And the first one of them, it's related to something that's called photogrammetry. And that means that we study image processing from the camera perspective. And that includes a lot of geometry analysis. And to do that, we're going to start by basically defining what a camera is, okay? And for that, we're going to talk about something that's called camera models. By the way, I have slides for most of what I'm going to cover here, but we have over the years received really bad feedback about using slides all the time, because that allows us to go really fast, but that's the problem, that it allows us to go too fast sometimes. It's difficult to absorb, so I'm going to use the board as much as I can. I will make, however, those slides available in Carmen as a PDF so that you have the main ideas and the main equations written down. They're also, of course, in the books that I'm going to be using, so you also have that information here. So if you miss something, either go to the recording in Carmen, or to the book, or to the slides, okay? And everything should be in there. All right, so let's talk about cameras. Let's start with explaining what the problem is with cameras. So I will usually draw maybe a camera like this, where I represent the camera as a box and maybe a lens as a triangle maybe, or I will just not even use that. Sometimes we will see them as this, but we'll get to that, okay? Now, obviously, this is not what a camera looks like these days. Most of you have a camera like this, right? Which is a little thing. I mean, this is the lens, but basically inside here there's a chip that takes the pictures. And we'll get to defining these things. That's pretty much what a camera looks like these days, right? The problem that we are interested in to begin with is that we are out here, right? Outside of the camera. And we are in the 3D world. right? And the camera gives us a 2D image of the 3D world, right? And it does this because it applies a certain number of geometric equations, right? That projects the 3D world onto a 2D plane, right? Now, the thing is that if I can model this camera, right, as some type of function, then I can go from this 2D image back to the 3D world, right? By simply applying the inverse of the function, the functional mapping. Okay, so far so good. Okay, oh, there it is. I'm looking for it. So I will usually talk about cameras in image processing. Oops. There are like this one, right? On a cell phone or on a photo camera or a video camera. But those are not the only devices that are available out there, right? There are many optical devices. For example, how many of you has had an X-ray taken in their lives, right? That's it, just 4? I say most of you, not all of you, right? Or an MRI, how many of you have had an MRI? Yeah, okay, or a CT scan and so on, right? All those things are imaging devices, right? All of them. And that means that all the things that we're going to talk about cameras applies as well to those other devices. Now, if we talk about X-rays, MRIs, CT scans, and so on, and we want to analyze these images that we get, then we talk about medical imaging because those are medical devices, right? And we have a course here in the department that is that covers that specific topic, right? Okay. And the same applies to many other types of devices, LiDAR, what have you. All right. In engineering, you have radars, telescopes, sonar. My goodness, the list goes on and on, right? So all of them are included in this. The word camera actually comes from camera obscura, which is a direct translation from French, would be dark chamber. It's when cameras were invented, they were obviously in France. They were called camera obscura or dark chamber because the way cameras were designed was by taking an actual box, right, or a camera, a room, a chamber, like this, that is completely devoid of any light, right? So this box does not allow, it's fully closed, does not allow light to get in. And if I have a light source here, right, the light just bounces back, right? It never gets in. Now, what you do is you put some film at the one end of the camera or the box, and you make a small indentation, a small hole at the other end of the box, and then light can go through that particular point, right, and get imprinted onto the film at the other end, right? That is the dark chamber that again, in French, would be called camera obscura, and the word camera just stuck, right? That's what we mean by a camera, a device in general that can take information from the 3D or 4D world, if we talk about 3D spatially plus time temporally, right? So 3D or 4D. So in general, we're going to define a camera as an imaging device that captures light and imprints it onto a translucent plate, the film, the CCD camera when we talk about this, which is usually located at the very back end of that box. Okay? Now, this hole that we are considering here in the camera obscura has to be a really tiny, tiny hole that allows to get in just one ray of light, right? Just one. And this is going to be called generally a pinhole. Okay? So far, so good? All right. Now, this will allow us to do the following. So what I'm going to do here is, let me redraw this again. So I have my camera here. Okay. My translucent plate or film at this end. Okay. And my pinhole right here. And now out here, I have my 3D world, okay? Now, if I have a light source, say here, right? Now, this light source emits rays of light in, say, this direction. That light hits the surface of a 3D object, right? And then it gets scattered, as we'll see, in many directions, right? Most of these directions are irrelevant to us, but one of these directions is this one that goes through the pinhole, right? And gets into the camera obscura and gets imprinted onto the film. And that's what we see in the image, right? So let's call this point right here capital P, okay? This is capital letters, capital P. Now, P, capital P, is given by a three-dimensional vector, x, y, and z, right? And I have my, say, a small p or a small p prime, if you will. I'm going to call this is a two-dimensional vector because now I'm only in 2D, right, in this surface. And let's say it has these two entries, u and v. That doesn't really work. All right, that doesn't work either. Okay. Have to use other colors. Okay. So capital P, x, y, z, 3 dimensions. Small p, u, v, 2 dimensions. So I can say that this is given in the real space of 2 dimensions, and this in the real space of 3 dimensions, right? Okay. Now, P, so let's see. Let me call, let's review 3D space very quickly. So if I have my basis vectors, I, j, and k, right? These are the 3 basis vectors of x, y, and z. that means that I need also an origin here, O. That means that I'm in the coordinate system defined by the origin O, I, J, and K, the basis vectors, right? Okay, so far so good, hopefully. So that's our coordinate system. Okay, so now I'm going to place, say, my O, my origin, right here at the pinhole. That's the origin of my coordinate system. Okay? And now I can define x, my variables here, x as, let's see, right here if I had a vector, x, right, in this coordinate system, what am I going to have? I'm going to be able to represent this as the projection of, so let me call this P, this point here, of that vector OP, right? This is the OP vector, projected onto I. This is equal to my x, right? And my y, which would be right here, that is going to be my OP vector projected onto J, and my z, my OP vector projected onto K, right? Yes? So I'm going to do the same thing here. I'm going to have my origin right here, and now I'm going to have my I basis vector pointing this direction, my J pointing up, and my K pointing inwards toward the image plane. Okay? This, remember, it's the film, which, or the translucent plate, which we're going to call the image plane. Okay? Now, let's see. Who can tell me in this coordinate system what, let's see, well, let's start with Z. What is Z here? What is Z measuring? Anyone? What's that? The distance from where to where?
3D world to camera.
Well, from what point in 3D world? From P, the distance from P to the camera, right? So this distance here, right, is Z. Right? So it's the projection of that vector OP, as we saw here, right, onto K, right? Right? Okay. Now this vector, or this dimension rather, that goes from O about the x direction, right? About the x, the k direction, the k axis, right? This dimension here, we're going to call it the optical axis. As before, as we did here, right? From O to P. Here I also have, this is O, this is P, right? So this here is the OP vector, right? And if you will, what did I call this? This one, let me call this one for a second capital P prime, okay? With coordinates x prime, y prime, z prime, right? So I'm going to consider this P point here according to this three-dimensional coordinate system. Obviously, that's a point in 3D space defined in this three-dimensional coordinate system, right? Yep. So far, so good. All right. Now, I also have then this vector right here that goes from O to P prime, right? What do I know about the OP vector and the OP prime vector? Yes. What's it again? Negative, a little more than negative. You're close. So the guess was that one is a negative of the other. That's not correct, but it's close. It's a scale version, or what's known as collinear, right? This one is collinear with this one, right? They define the same line, and that's the same as saying that one is scalar version of the other, right? So let's write down this equation. So now I have right here, I'm going to copy this here. OP is, actually, I have it in my notes the other way, so why don't I follow my notes? OP prime equal to lambda OP, same thing. So I have OP prime, which is x prime, y prime, z prime, equals lambda times x, y, z, right? Right? So that means I can write x prime, x prime equals lambda x, y prime equals lambda y, and z prime equals lambda z. Okay. So I have a system of three equations. Now remember, this is z. Anyone can tell me what z prime is? What's that? Okay. I haven't explained what the focal length is, but yes, that's correct. Anyone else? It's the distance from where to where? From the pinhole to the image plane about the k vector direction, right? Or the optical axis. So here, that was about the optical axis, the z direction, when I project OP onto k. And this is the same for OP prime onto k. So this distance from the image plane to the origin or pinhole O, that is z prime. Okay? Now, as someone just mentioned, this, we're going to call it f, and this is called the focal length of a camera. All right, so let me substitute this here. Now the focal length, that is given, right? This is a value that is given because this is fixed from the pinhole to the end of the chamber, right? This is a distance that is fixed by the design. So if I have this phone here with its camera, the distance from the pinhole at the very front and the film or CCD at the very other back of the chamber, right? That distance is fixed. Now, if you look in the manual of your phone or your camera, it will say what that distance is, okay, in these specs. And if you buy a very fancy camera, it will give you a lot of information about it, and we'll see why this is important. All right, so with that, I can write that my lambda value is either x prime over x or y prime over y, or the same as f prime over z, right? They're all the same. You can choose whichever you want. I'm going to use this one, the last one, as the value of lambda. And therefore, I can write that x prime is equal f x over z, y prime f y over z. Right? Yes? Okay. This is one of the most fundamental equations we're going to be working with. This is projective projection, okay? Now, my x prime, y prime are nothing else than the corresponding small p vector that we were talking about. These are the coordinates of the image where my point is imprinted, right? Where my light source gets imprinted into, right? And x, y, and z, where the 3D world point is located at, right? So depending on the focal length of a camera, I'm going to get an image or another image, right? I'm going to get different images as I change the focal length. Make sense? Also, as I change the z of that point P, right? I put the object farther away from the camera or closer. That will also change how the image is created in the image plane, right? So how does this affect? F, it's a multiplier, right? So the larger f is, the bigger the number x prime is going to be for a fixed x, right? Same for y prime and y. Z, on the other hand, is a divider, right? Inverse proportional. So the farther away this object is, so the larger z is, the smaller the value x prime and y prime are going to be. You see that? So one is inverse proportional. The other one is proportional too, right? Now, f, you can already guess that I can use f, if I vary f, as a zoom in or zoom out variable, right? So if I want to see objects that are really far away in large formats, I need a very long chamber, right? That's why telescopes are so large, right? Because the longer the chamber, the longer the focal length, the bigger objects will look, no matter how far away they are, right? Okay. So I'm going to write my small p that we had as, this is small p, not capital P now, x prime, y prime vector, okay? Now the perspective model, projective projection, the perspective model that we're going to call this, the perspective model is one of the most famous and useful models of cameras that we will discuss. It seems simple, but it's a set of nonlinear equations that are going to give us a lot of trouble, okay? So we'll have to work with that. We will later see how we can model cameras with lenses as well. We are, however, not generally going to use those models because models with cameras, models with lenses are really, really difficult to work with. There are good approximations that we can work with, but even those approximations are really hard to work with. So we're generally in image processing and computer vision tend to use the pinhole camera model that I just described here. Now, in many cases, even this perspective camera model is a little too complicated to work with because obviously they are nonlinear equations after all. And we will also, therefore, discuss simplified models of this, okay, that we will tend to work with whenever possible. All right, so let's see, let's start with some properties or a better understanding of the perspective projection camera model. All right, so we have already noted that if I change the focal length, I can see objects that are really far away, larger. And if I decrease that focal length, I can see objects that are really close, smaller, right? Okay. Obviously, if I move the object further or closer, that has the same effect. The further the object is, the smaller it will look. The closer the object is, the larger it will look, right? So one is proportional, the other one is inverse proportional. What else can you tell me about that camera model that is interesting to observe? Anyone? Let's see. Let's think about this. Let's consider that case that we were looking at. So we have a three-dimensional object here, right? This is a 3D object. And what I'm going to do, I'm going to have my camera here at the very end. With the pinhole, remember the pinhole, it's the origin. This is where I place the origin of my coordinate system, right? Now again, as before, I have my three basis vectors, I, J, and K, pointing in these directions, right? I have, as we have done before. And what else are we going to do? So we have our focal length. And the focal length, F, it's the distance from the origin to the image plane. So that distance here, right, from this to here, this is the focal length F. And now if I have, say, 3 points, let me call them P, Q, and R. P, Q, and R. Okay, so these are three-dimensional points in the world. And if I project these 3D world points onto the image plane, what do I get? Let's see. So P is going to be projected here as capital P prime, right? So far, so good? Okay. Now let's project, let's do R. We'll do R next. This one here. This is R prime. And now let's do Q. This is right here, right? So I will observe the 2D image of that object, right, in 2D right here. But something very strange has happened. Where is it? It's inverted, right? It's upside down. Whoops. So now all of a sudden, the image at the back of the camera obscura here in the film, it's inverted compared to what I have out here, right? Oh, that's a little inconvenient. Means, who cares, right? I mean, it doesn't matter what's up and what's down, right? As long as we know what's up and what's down. The problem is we have this coordinate system here, right? And that means that we are stuck with working with that inverted image. That, however, has a very simple solution if we feel more comfortable. We don't have to, but if we feel more comfortable working with right side up images, we can do that with a simple trick. Anyone can tell me what that is? Yes. Right. So note that k, the basis vector k, points inwards, right? So that means that this psi of k, right, the z of our object is negative, right? It's a negative number. That's what's causing that inversion, right? So a simple trick that I can do is I can consider not this f, but its opposite in front, right? It's negative f, if you will. So negative f, if I keep x and y constant, this is the same as copying the image plane up here in front. So that plane is going to be parallel to the image plane, but it's going to be in front of the pinhole, not after or behind the pinhole, right? And this just is a negative sign that I need to change in z, right? It's the same image. But note what happens. When I do that, now P is over here, Q is over here, and R is over here, right? And now all of a sudden, the object is right side up. That's it. It's that simple. Just not to be confused, we'll call this P prime prime, Q prime prime, and R prime prime, okay? Just not to confuse them with the P prime, Q prime, and R prime that we already had. So that's a very simple trick that we'll use quite often. This is called the virtual image. Now, the reason this is called a virtual image is because that image obviously does not exist. I don't have that image, right? When I capture the image on a camera, I get the inverted image. But for me, mathematically, to convert this image in a right side up image is as simple as changing a sign, right? Okay, what else can you tell me about perspective projection? So we've said, let's think about this again. We've said that for a fixed f, for a fixed focal length, the farther away the object is, the smaller it looks, right? What might happen with this? What might be the problem that we have to deal with when this occurs? Let's draw this again. See if we can understand this a little better. See, how am I going to do this? Let's do this. I'm going to draw a plane here. Now consider this plane the floor of this room, okay? This is our ground, this floor. So obviously I did the best I could, but this is what's supposed to mean, right? And now our image plane is going to be orthogonal to that ground, okay? So the image plane, I'm just going to draw it here. Okay. And this is orthogonal to the ground, okay, to the floor. Now, we're going to consider our pinhole, say, over here. So this is our pinhole O. And now I'm going to consider also two objects. One is this object right here, and the other one is, say, this object right here. Okay? I'm going to call this first object C, or this vector that I have here, C, and this one B. Now, let me draw a line here. This line is parallel to that line of the image plane intersecting with the ground, okay? And another parallel line here, okay? All parallel to the line intersecting the ground and the image plane. So we'll call these L1 and L2. All right, so let's get to work. What happens when I take a picture of this 3D world right here? So let's start with C here. I'm going to get this through the pinhole like this, right? And this is going to give me the first image of the first object, which is going to be like this, C prime, right? And obviously, if I had this line right here would be the image of this line, right? Right? You see that? And now let's take the image of this other object right here, right here. And that means that I'm going to have this object right here, B prime. And that line right here is going to be the image of this line, L1, okay? So I'm going to call this L1 prime, L2 prime, in the same sense that I call this B prime and C prime, right? Now, what just happened? Note that the size of this C prime, you see this C prime here? You see this? It's exactly the same size as B prime. You see that? So the size of C prime, it's identical to the size of B prime. Now look at this, identical. But how about C and B? C is much smaller than B. How is that possible? Well, that's perspective projection. The further away an object is, the smaller it looks, such that objects of different sizes may look identical in the image plane, but be different, of different size in the 3D world, right? that is hugely problematic. I see people taking pictures. I have better drawings of this in the slides posted online. I mean, you're welcome to take pictures, but honestly, the images online are computer generated, and it doesn't matter how hard I try, I can never do as good as a computer, right? Okay. Now, in the same way that we have this problem, we can have an even more interesting problem. So if I have to copy this, if I had to copy this again, let me copy this here again. Oops. Okay, the pinhole, and now I'm going to consider, same as before, these two lines, L1 and L2. But now I'm going to have two objects. C is going to be the same one that I had here before, the exact same vector, C. And I'm going to have another vector, say here, A, okay? Such that A and C, you see that? Say C and A are exactly of the same length, okay? And now let's repeat the process. What happens if I do a projection of these through the pinhole? I get this vector here, and I get, let's see, this vector here, right? Whoops. Okay, so I have, this is A prime and C prime, right? With the corresponding lines, L1 prime and L2 prime. And now C is smaller than A, right? The opposite happened. I started with two objects of the same size. I ended up with objects of different size in the image plane. That's what perspective projection does, right? And that is because of this nonlinearity. Where is it? Right here. This nonlinearity right here, where I divide by the z value, right? Now, in the slides, you have the classical example where you have the tracks of a train, and they look like this. Right? So these are the rails of the train, and this is the wooden thing in between, or metal thing in between the rails, right? That maintains stability, what have you, right? And the image of the rails of the train looks like this, right? If I plant myself right here in the middle and I take a picture, classical picture. You can do that in a road, right? In a long, straight road, and you'll get this image, right? And this piece of wood right here will appear much smaller than this one, right? But obviously that's absurd. They are the same size because the rails are two bars parallel with one another, right? So this is a very important observation. Parallel lines in the 3D world are not parallel in the image plane, or they don't need to be parallel in the image plane. Although they are, we'll get to that, right? But you may think that they're really not, right? Okay. In general, what is going to happen, let's see, if I have, how am I going to draw this? Let me make my attempt. Again, better drawings in the slides online. I'm going to try my best here. compounded with the difficulty of drawing these things, the board is 2D, the world is 3D.